Hello, and thanks for joining tonight's TI Technology event hosted by Texas Instruments, where tonight we're going to take a look at exploring what's typical using graphical displays of data. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists for tonight, Gail Burrell and Robin Levine-Wissing. Gail was a secondary teacher and department chair in suburban Milwaukee, Wisconsin for over 28 years. She's currently a mathematics specialist in the program for mathematics education at Michigan State University, and she served as Gail is currently a senior mathematics advisor for Texas Instruments and a T-Cube national instructor. Her research interests are statistics education, the use of technology in teaching secondary mathematics, and issues related to what it means to teach mathematics. Gail, thanks so much for being with us.
Thanks, Mike. I'm glad to be here.
And Robin taught high school mathematics for 38 years. She taught AP statistics since the course began in 1996. Robin's been a reader and a table leader at the annual reading of the AP exams. She has been presenting TI Technology workshops since 1993 and College Board AP workshops since 2000. Robin co-authored an AP Statistics Test Prep book in 2006, and she currently teaches statistics for the University of California Riverside Extension Program. Robin, thanks for being with us.
Pleasure. Happy to be here.
At this time, Gail is going to discuss our agenda.
Thanks, Mike. So tonight what we want to do is think about what is typical and what is not. In the process, we're going to think about using data to make decisions, and different ways to make decisions depending on the context. We're going to be comparing distributions, talking about communication and how important that is in statistics, teaching statistics. Think a little bit about misconceptions. If we have time, talk a little bit about cautions in using real data. And then we'll share some online resources with you, and hopefully, you will be able to win a registration for two to the international conference that's going to be held in March.
Thanks, Gail. And Robin is going to discuss our expected outcomes.
We're going to explore graphical representations of data sets, thinking about shape, center, and variability. Learn how TI Technology can give students meaningful opportunities to develop an understanding of what's typical and what is not for a particular given set of data.
Thanks so much, Robin. Gail, it's all yours. Feel free to share your screen.
Okay, I'm going to share my screen right now, and we'll get started with thinking about what is typical and what is not. And so, Robin, can you see my screen?
I can.
Okay. So the story here is in the data, and we're talking about shape, center, and variability as the three ways to kind of help us think about what is typical and what is not. And the first set of data we're going to look at are some pretty standard data, the effect of exercise on heart rate. And this data comes from some British children aged 9 to 11. And we're going to go and we're going to actually look at that data that has been pasted into a just a regular Word file. I'm going to copy that data. Okay, and so I'm just going to copy it out. And then go to my TI-Nspire file, and I'm going to paste that data right into the file. Then I'm going to go up and I'm going to label it. So this is going to be beats before exercise. And this is going to be beats after exercise. Uh-oh, what happened? All the data disappeared. And it's back. Okay. And so now what I want to do is get a picture of the data. And so I'm going to insert a data and stats page. and I'm going to look just at the beats before. And so here we have a dot plot that shows us what the distribution looks like for the beats for these students before exercise for their heart rates. And one of the first things that we ask kids to do is to talk about what's the shape, what does that look like? And the shape here is kind of mound-shaped and a little bit symmetric. And that's kind of an important thing that we want kids to think about. Mound-shaped and symmetric, and we need both of those. And this is how they start in middle school when they talk about data distributions. They have them talk about mound-shaped and symmetric, and they avoid the word normal until kids are ready to think about what being normal really means. Normal means more than mound-shaped and symmetric. It's also important that kids understand that it's not enough just to be symmetric, because you could have like a U-shaped data distribution. It's also not enough just to be mound-shaped, because your mound shapes could be located at one end or the other. So you kind of want to have both, mound-shaped and symmetric. And then you want to talk a little bit about what you think is typical. And the typical is kind of a cluster of what you're looking at. And one of the things that we try to help kids understand is we want to get some kind of a measure of center or typicalness. And typically, what we use for that is either the mean or the median. And I can kind of estimate just by looking here that I think that center is somewhere right in here. Looks to me like if I were to count, I could count to get the median, or I could just kind of estimate what it looks like. So I want my students to be able to talk about what's going on here. What are they seeing? And here they're seeing that typically the heart rates, the beats per minute, are between about 76 and maybe 91. There's some on either end, but that's kind of the typical one, with maybe the mean or the median somewhere around 84, 85. And because the distribution is mound-shaped and pretty symmetric, it's not surprising that the mean and the median would be pretty similar. So it's kind of where we're thinking and what we're looking at here. And so now I want to say, okay, a few kids have their beats per minute as many as 106 beats per minute, and one of the students says it's few as 64 beats per minute, which is kind of gives us a notion of the spread or the variability that's going on. But we also want to think about the variability away from the center. So if this is our median or our mean, we're trying to figure out how far away the data points are from that mean or median. And that gives us a way to measure kind of a sense of the variability in these pulse rates for the students, so we can get a better grasp of what we're thinking about in terms of typical. And so one of the ways that the new Common Core has suggested that we pay attention to is thinking about the mean absolute deviation. And I've been doing this with my own students and finding it actually a really great way to introduce the whole concept of variability and also leading to the standard deviation. But the mean absolute deviation is just the number of deviations each of the data points is from the mean. So you can see the distance between the data point and the mean for each of the data points that we have. Summing those all up, taking the absolute value and summing them up, gives you a sum of the absolute deviations, and taking the mean of that gives you a kind of a typical or average deviation for this set of data. So that gives me a sense, and in this case, if I would do all of that, I'm going to find that the mean absolute deviation is about 8. So typically, there's between about 8 above my 84 and 8 below my 84 gives me a really good typical range for what the pulse rate is for these students before they exercise. So then I want to add in, I want to look at what happens after they have done the exercise. What is this distribution going to look like? And it's a good thing to ask kids to predict. What do you think is going to change? I'm going to add an X variable in here, but I want my students to think about, well, what might be different? Do you think the distribution will be pretty much the same, or is it going to change? So I'm going to add another variable, and now I want to add the beats after, and now I have a very different looking distribution. What has happened to the pulse after the kids did some exercise? So this distribution, the kids have learned to call skewed, where the tail is off to the low end, and the kind of a cluster of beats per minute are up at the upper end of this distribution. Notice that it's much harder now to talk about what's typical. Robin, did you want to say something?
Well, when we have students looking at the two distributions at the same time, we also want them to look at comparing that variability between the two. And so students would typically say with the beats before up on the top display that it has much lower variability or smaller variability, smaller range than the beats after. And you might ask students, why do you think that is so? So just, yes, we're looking at all these attributes of the graph, but give students a chance to articulate why do you think that would be so.
Right, and notice that it's very much more difficult to figure out where the typical is. Some of my students want to say that typical is here between 160 and 180 beats per minute, and that's because they're actually thinking about the cluster and thinking kind of in a modal way of trying to describe the data. And that's why it's so important that they think about the mean and the median. And here, actually, the mean is about 145. The median is 152, okay? So the mean is a little bit lower than the median, and that's very logical because the tail is pulling the numbers down. But it's good for kids to think about that and to know that here I have this mean, and my spread, my deviations from the mean is much larger. As a matter of fact, if you were to figure out the MAD for this, it's 23. So I'm going, if I were to go 23 units above and 23 units below, I've got a much larger spread, almost 3 times as large as a spread here. And again, what Robin is saying is get the kids to think about why might that be. Make sure that they understand that the lowest kid here is not necessarily the lowest kid here, that there's not a correspondence, and that they are able to talk about what's happening to the distribution as a whole, not just as for an individual student. Any more questions here, Robin, before I move on to?
Yeah, the other comment I'll make is another example where you can do this with students and have 2 different displays of the same type of data is when I work with students, I will display test scores of 2 different classes, or I might give them the mean and what the deviation is from the mean. And I would say, well, which class would you want to have your test score? So for example, if you look at the top display, and since there is less variability here, if you were given the mean and it has very small deviations from the mean, you might feel more secure about your test score. Whereas if you look at the lower graph, the beats after, if you were given the mean, but because there's such a large variability, your test score could be all the way down in that smaller area where the lower values are. Maybe you're not as secure. So it's just looking at data that even if your means are similar, but the variability is quite different, that you could have much lower or much higher values in there.
Great. And one other thing that you kind of want to pay attention to is that the mean, in this case down here it's 145, that mean is really the balance point of the distribution. It balances the deviation, the positive versus the negative deviations. And those of you that have an 84, one of the great ways that you can actually find or mark that balance point is to use plot point. I can't do that here on the Nspire, but on the 84 you can plot a point and then move that point to where it looks like the balance point. So kids get familiar with thinking about what that balance point ought to be, where the deviations above the mean and the deviations below the mean balance. And they can do the same thing here. So using that plot point functionality on the 84 is really a nice thing. I kind of wish the Nspire had it. Okay, so let's go to another set of data here. This is back to this communication thing. So one of the things that my students do all the time, especially at the beginning of the course, is when I ask them to describe what's going on between the exercise before and after, they give me this set of statistics that they've calculated. And so this is what I'm apt to get. No words, just this list of statistics, and any interpretation is just not there. And so I'm really very pushy about trying to get my kids to use words and numbers to describe the distributions that they see, so that they should be saying the typical pulse rate before exercise was about 86 beats per minute. The typical after exercise was about 145. So there was a great increase in the mean of the distributions after exercise. The spread went for the MAD was only 8, whereas the spread or the variability after exercise, 23, that's where we're using the MAD. So that there was a drastic increase in the difference between the kids after they had their exercise. So I want my students to actually be able to make those kinds of statements and make sense of them. And this came from the AP listserv, and it was one of the things that Dave Bach said, that this business about having them write, they've done a lot of calculations, but rarely have they had to write clear, complete, concise, and in context sentences. So it's really a good thing to get them started off that right at the very beginning of the year, knowing that this communication is such an important issue in teaching statistics. All right, here's another data set. And this one is the number of words a class of 32 students could read at the end of the 2nd grade. And the question that I posed to my students were, are any of the students extremely poor readers or extremely good readers for their grade level? And explain why. And so again, here we want to think about what is typical. How might we do that? And we can actually count or estimate or look for our balance point. So I could kind of make an estimate that maybe it's right in here. But the question's focusing not only on what is typical, but on whether any of the kids are extremely good or extremely poor readers. And one of the problems with my students is they often think that just because somebody is the minimum value or because somebody is the maximum value, can read the most number of words, they're going to be extremely good or stand out. And that's not the case at all. We need to have some kind of, in statistics, some kind of a way to measure whether or not something is extremely different from all the rest of the data. And so we're really basically looking for an outlier, but we need a rule or a way to figure that out. So I'm going to actually add a page in here. So I'm going to go insert a page. And I'm going to insert that page. It's going to be a data and stats page. And I'm going to reproduce my words per minute here. Okay? But then I'm going to go and I'm going to add a split screen. I'm going to add on this page a calculator. And I'm going to go to menu, and I'm in statistics, and I'm going to do stat calculation, and I'm going to do one variable statistics. I only have one list. I'm going to check, and that's words per minute. I'm good with that. And I now have all the kind of one variable stats you would ever want. So the mean number of words per minute is about 90. That balance point is about 90 words per minute. The median number of words per minute is 84.5. So 90, here's down here, 84.5. And I can get the standard deviation, I can get the IQR by the medians. And so I'm going to look at the standard deviation here. We'll use 15. It's about the standard deviation I want. And I'm going to now close this. And you guys have to help me remember that the standard deviation was about 15 and the mean was about 90. Because I'm going to make a picture of what that looks like. I'm going to go to statistics. Get me back on this page. I'm going to go to Analyze, Plot Value, and I'm going to plot that mean, which we said was 89. Okay, it's about 90. And so now I have, and again you can kind of see that idea of balance point, but now I have that mean plotted there. And I'm going to look to see what kind of variability do I have. And the way I'm going to do that is I'm going to plot, again, Analyze, Plot Value. I'm going to plot standard deviations above the mean, okay? So I'm going to actually lost it. Analyze, Plot Value. I'm going to plot 129. If I add 1530 to my 89, I get that. And now I could actually add 2 standard deviations below the mean, but that's going to be way off here. And so I'm not really interested in that one because clearly that would not be that 65 would not be an outlier or extremely different than everybody else. But up here, it looks like this 130 is past the other scores. It's 2 deviations, 2 standard deviations above the other scores. And so I'm going to actually arbitrarily say that anything that's more than 2 standard deviations above or below the mean is going to be an outlier. So I'm going to say that this one student is, if in fact, reads better, more words per minute than the rest of the students in that class. But the important thing here is that I've found a way to measure when I think something is going to be extremely different, to be an outlier. So I'm not just using an endpoint. I found some way to actually come up with a measurement. And the measurement choice that I used was 2 standard deviations away. This is kind of arbitrary, but it at least gives me a rule, and a rule that I can communicate to everyone else. Robin. And
as well, it gives a very good visual for students because we do want students to communicate, and when they have a picture, sometimes it is much easier for them to communicate. So the visual piece of it is excellent.
Yes, I think the visual piece is absolutely critical. Otherwise, kids are just playing around with numbers and they really don't know what they're doing. Okay, so I want to do one more thing with this, and I'm going to go to Menu, and I'm going to go to Plot Type, and I'm going to make a box plot. And the box plot gives me the 5-number summary. So I've converted my dot plot now into a box plot where I can now see the median is 84. Now remember, it's a little bit lower because actually I have an outlier. So it's reasonable that half of the data points, half of the words the students can read fewer than 85 words per minute. Half of them can read more than 85 words per minute. But on average, the mean was 89 words per minute. So we're kind of making that observation by thinking about the numbers and thinking about the graph that we're looking at. So this also, using this box plot, it shows me that in this case, the 130 is still an outlier. The 122 is not an outlier. It just happens to be the last data value before that outlier. So if I were to go back to the dot plot, there would have been a dot right here, last data value. Sometimes kids wonder what that point represents. But that gives you 2 ways to actually describe what's going to be an outlier. this outlier from the box plot comes from 1.5 IQRs. So I find the interquartile range, put 1.5 of those interquartile ranges above the upper quartile and below the lower quartile, and check to see if something is bigger than that or smaller than that, and that gives me an outlier. So I have two kind of legitimate ways to define whether something is extreme and whether some of these kids are actually reading more words per minute or reading fewer words per minute. Okay, Robin, anything else, or are we ready for the PowerPoint?
We're ready to move on. Yep.
All right. So I'm going back to the PowerPoint here, and we've done the working with that data and that data. And now we're going to look, Robin's going to talk about some problems from the AP exam. Robin?
Well, using problems from the AP statistics exam in stats classes is very, very helpful because students get experience with what the expectations are in responding to a problem. And the quote from Dave Bach that Gail brought up earlier was that communication piece, that students really are not being asked to communicate or give explanations in classes before they get up to the AP. So we would love for students starting really in 6th grade, 7th grade, and 8th grade to be able to communicate from various problem situations. Now, AP problems can be used in 6th grade and 7th grade and 8th grade, 9th grade, because you can take a look at the AP problems. You can modify them for the course you're teaching, whether it's modifying some of the mathematics that's being asked or some of the types of questions. But I've worked with middle school teachers and junior high school teachers where we've taken AP statistics and AP calculus problems and revised them a little bit for that grade level and really got students to start using visualizations, looking at displays, and writing this communication piece. So these two problems that we're going to look at today are two that I used in class. My favorites, especially the gasoline additive ones, you can see it came from 2005, and I've used it for many, many years. So let's take a look at that one first. So what students were asked? Students were given summary statistics, and Gail showed you some of those summary statistics when she used the Nspire and called up the one variable statistics. So students were expected to construct that graphical display that you see there. They were expected to label additive A and additive B. If students do not label their displays, they do get a deduction. So this is the model of what the display should have looked like. And that was part A. In part B, it says two ways that the effectiveness of the gasoline additive can be evaluated are by looking at either the proportion of cars that have increased gas mileage with the additive or the mean increase in gas mileage with the additive. So Roman numeral 1 says which additive, A or B, would you recommend if the goal is to increase gas mileage in the highest proportion of cars? Explain your choice. Now that's the key there, explain your choice. In English classes, students read novels or they discuss plays, and they are very often asked, compare and contrast some characters. Well, comparing and contrasting, you have to appeal to both sides. And this is the same thing in statistics. Explain your choice. And we get many, many students that will say, I choose additive A because, but they never go back and say why B wasn't chosen, and that's really important. They have to appeal to both sides. Why are you making the choice for the one you are taking, and why are you not making the choice for the one you did not take? All right, so if we look at the next slide, the model solution, now these are all available on AP Central, which is the College Board website where you can view all past AP problems and their solutions and student examples of solutions. So they give a model solution. Now the model solution does not mean that we expect that exact solution for all students. This is just a model, and when readers are trained to grade these exams, we look at many, many, many student solutions to see what would be acceptable. So again, this is just the model. So part B, Roman numeral 1, additive A is better at increasing the mileage in the greatest number of cars. The mileage increased for at least 75% of the cars with A, whereas the mileage decreased for more than 25% with B. So you can see the communication part. We've talked about why we took A and why we did not take B. Now, Gail's going to point, and if you look at the at least 75% of the cars, well, the median is at 0, which means there is no increase of gas mileage. And right there is the first quartile where Gail's indicating. And so that means that 75% of the data is to the right of that. So about 75% of the cars got an increase in mileage with A. Whereas with B, the reason is that the mileage decreased for more than 25%. So you see right where that median is, again, the 0, there's more than 25%. It's more than the first quartile below that 0. It's almost right up to the median, so maybe closer to 30, 40, 50%. So that was the reasoning for the solution in part B. Okay, next slide. All right, so this one wanted to know the higher mean. Which one would you take? So the model solution says additive B appears to produce a higher mean mileage gain than A. The box plot for B clearly shows the distributions is skewed to the right, which will pull the average towards the larger values. And Gail had shown you with the beats per minute after the students exercised on that dot plot, how it was skewed in the other direction, and the mean was pulling, the skewness was pulling that mean down to the left. The mean difference for B will be substantially greater than the median of 1. On the other hand, the distribution of differences for A has much less variability as seen by comparing the lengths of the two boxes. Now, the boxes are that middle 50% of the data. That's kind of what's typical, that middle 50%. That's maybe what you would expect. So if you compare the lengths, you see that B has much more variability in that middle 50% than where A is. So the mean difference for additive A will be less than the median of 3. So if you want a higher mean mileage, you're going to go with B because the mean is certainly much greater as shown in the graphical display. Next. All right, then each year after the exam, the chief reader puts together notes on things that students typically did or did not do to make suggestions for teachers. Teachers can use these notes to help guide their courses for the following year. So obviously the intent of the question was to assess students' ability to use summary information, and students were asked to interpret the information provided in the box plots by making recommendations based on the two goals. Common misconceptions from students occur when students make a choice and are not able to adequately articulate why they are making that choice and at the same time why they didn't choose the other. So I'm just going back to what I mentioned a few minutes ago, is make your choice, defend your choice, but then you have to talk about why you didn't take the other choice. That is definitely required to get complete response, and you can be working on that with students at grade levels way before they get into high school or way before they would get into an AP class. Gail, did you want to add anything here?
Nope, it's great.
Okay. Let's take a look at the next problem, salary increases. So this problem basically is looking at two corporations, and they had starting salaries that were the same, and this display is 5 years later. So this display is the salaries 5 years later. Both corporations, it said in the stem of the problem, the starting salaries were $36,000. This is now 5 years later. So part B, suppose both corporations offered you a job at $36,000. Roman numeral 1, based on the box plots, give one reason why you might choose the job at A, and Roman numeral 2, based on the box plots, why you would accept the job at B. And notice the question is asking based on the box plots, which means you have to appeal to something statistical and graphical when you give your solution. All right, next slide, please. So when you look at the model solution, if you look at Corporation A, what do you notice about Corporation A that's different than B? Well, Gail's pointing to that. We've got some very high salaries out there. And on that type of box plot, those are considered outliers, which is not necessarily typical. So some people might want to go to work at Corporation A because there's a possibility or a chance of making a very high salary. Now, if many students said, I want to go to Corporation A because I can make a high salary, well, there's a big difference between I have an opportunity to make a large salary or I could make a large salary and I would make that large salary. There's no guarantee you're going to get that salary. In fact, where Gail's showing the on the graph all the way down to the left, you could still be down there 5 years later. So a student had to say, well, I'm going to go to A because they have many salaries larger than B, which is true from the display. And what's your reasoning? I might or I could make a larger salary at A than at B. All right, let's take a look at why you might go to Corporation B. When you look at Corporation B and you look at the variability in that box plot, you can see that Corporation B has less variability than A. The other thing that hopefully students notice is, remember, this is 5 years later. Is anybody at Corporation B making the starting salary? No. Everybody at Corporation B has gotten a raise. So one good model solution is I'm going to Corporation B because everybody got a raise there. So I know I'm going to make more than $36,000  5 years down the line. I mean, that was a very good solution. Another solution about why you could go to B is because there's less variability, you won't have that low salary there. Everybody got a raise, so multiple reasons why you could go to Corporation B. But remember, both solutions had to appeal to looking at the display. You have to come back to look at the display. Okay, next. And then again, here are some notes on that question, which of course you can pull these off of AP Central, of what some of the goals were and what students did. And if you look carefully at the first bullet in Part A and the first bullet in Part B, they both talk about students didn't communicate clearly. And that's the key to this, is that communication, the writing about what is needed. In this problem, they needed to make a choice and give a statistical reason. And why is that a big deal? Well, I'm going to Corporation B because it looks like I will definitely get a raise. Nobody is making $36,000. Or I want to go to Corporation A because they have some higher salaries than B, and I have a chance at making some of those high salaries. Okay, next.
Just one thing.
I'm sorry.
I want to point out that the fourth bullet, some students omitted the context. That's back to that same thing that my students often do, is just they crank out all sorts of numbers but omit the context. So even on the AP stats, they're still doing that. So just want to point that out about how important it is that they use words in their communication along with their numbers.
Thank you for bringing that up, because context, if context is not there, they do get a deduction. So thank you for bringing that up, Gail.
Okay, good.
All right, next. All right, and another piece that was brought up is the complete shape information cannot be necessarily determined from box plots. The only definite measures can be learned from the box plots or elements from the 5-number summary. And so if you look at the next slide, here's an example of 2 different sets of data that, when you look at the box plots, they look pretty similar. But when you look at the histograms on the top, one of them clearly looks pretty uniform, and the other one is symmetric. They're both symmetric, but the one on the right is bimodal and clearly not the same shape as the one on the left. So you have to be careful discussing shape with box plots because you're not sure where within the whiskers or the box or within each of the quartiles exactly where all those numbers fall out. They could be all clustered together and you would not necessarily know that. So sometimes a dot plot and a histogram gives a better view of that and will confirm the shape of the data for you. Thank you.
Okay, great. So we said we would talk a little bit about misconceptions, and you probably got some of those we mentioned along the way. Kids misuse the word normal. They think anything that's round-shaped is normal. Forget about the empirical rule that has to be there. 68%, 95%, 99.7% of the data, and that's a key thing to help to make sure that you actually have a normal distribution. So it's not enough to just look at a mound-shaped distribution and say, ah, yeah, it's normal, or even mound-shaped and symmetric. You have to have that 68, 95, 99.7% rule applying to the data. They don't view the spread from the mean or the median. They kind of think of variability as just how things are all just laid out, or actually even sometimes the height of the bars or the height of the dot plots get mixed up with the idea of the variability. So they lose reference to the context that Robin and I both talked about that, and they can't read between the data to summarize and compare, nor beyond the data to make some kind of an inference. So these are all things that we as teachers should actually be trying to make sure that our kids understand these are potential misconceptions and help them work through them. The box plots are a whole different kettle of fish. I'm actually really concerned that in the way the Common Core has laid it out, the kids are supposed to be learning about box plots when they're in 6th grade, and it feels to me okay for them to start making box plots, but it's really, really difficult to interpret box plots for all the reasons that Robin has already said, and there's lots of data from the research that talks about problems that kids have with box plots. And so we're going to go and look at kind of an intervention that we might be able to use with the box plot. And I'm going to go back here, and I'm going to go to a TNS file called box plots. This TNS file comes from Building Concepts, Statistics, and Probability, which is actually available on the TI website under Building Concepts. And there's a whole bunch of activities that are useful for helping kids think about and develop understanding of box plots. So Robin, tell me what to do.
Okay. So here we have a distribution of data on text messages. And so obviously you can ask students, where do you think the center of the distribution is? What do you think about the shape? And one of the things sometimes that we have students do is look at the box plot of this data at the same time. So Gail is going to have that appear for us. All right. And what's kind of fun for students to do if they have this is, could you move any points in the dot plot and not change the box plot at all? And so that's where, when you look at that box plot, you are not sure about what's going on behind the scenes there and how the data is distributed. And so if you look at the points around 62, 63, 64 in there, could Gail move them somewhere else and not change the box plot? So this would be a great kind of discovery for students to play around with this a little bit. And if you look at what Gail's doing, she's taking these points and moving them, and it's kind of creating another cluster down there in the 40s, and she had them all the way to the right before in the 80s, and so now there's nothing in the 60s. And Now, if students were just to look at that dot plot without the box plot, they might have a whole different description about what they're seeing. So the students can take the points and move them around and see how the box plot can stay the same, or which points do I move, what Gail's doing right now, will make a change in the box plot. Now, if you look at, Gail just took that one point, and it's making some big changes. So before, she took 3 or 4 points with no change, and now 1 point with a change. So it's a very good discovery activity for students. And there she's moving things to make the third quartile, the variability, a little bit larger, a little bit wider.
I'm actually trying to get the to look kind of symmetric.
Okay. That looks pretty good.
And so,
that
it's
go ahead.
Mound-shaped. Kids will think that it's mound-shaped without understanding. You can't tell.
So it's very important that they actually look at a type of dot plot really shows where those values are. Even if you look down by number or by 20, you can see all those data points are stacked up there by 20. And so you've got a whole cluster there in one spot. You would not notice that in the box plot, that all those 21, 21, 21, 21, 21. You just would not notice that that was even happening if you just had the box plot in front of you. All of those points that Gail is highlighting.
Right. So it's really good to give kids practice in playing around trying to create different shapes and distributions. Don't you actually do this in an activity, Robin?
I'm sorry, say that again. I lost you for a second.
Don't you actually have your students try to create shapes?
Yes, yes. One of the activities is I give different scenarios for students, and so they're in groups of 4. And they get a little envelope and they open it up, and the activity might say, construct a plot such as that the points do have this attribute. And then another group gets something different. So each group gets different data, and then they rotate through, and they have to be able to describe the data. Well, just looking at the box plots, they can't necessarily describe that data.
And I've actually tried to get my kids to say, okay, who can make this into a uniform distribution? Who can make it into a mound-shaped symmetric distribution? All for the same box plot without, you know, like you could kind of see I could kind of keep moving these guys over, and I could start to get that pretty uniform. And the box plot won't change at all.
Hopefully, after students work through this type of activity, they will not rely on the box plot for their shape of the distribution.
And so that's not to say that a box plot isn't really important, because it turns out really, in the cases that Robin was showing you from the AP exam, that box plots are really an excellent way to compare data sets. And they're also really a good way to find out if we have outliers.
Another example I've used very quickly is we have the Olympics every 2 years now, and I have students take different sports, male and female, where they've competed in the same type of event, like swimming 100 meters or running the mile. So you want to take an event where the men and women run the same exact course. And I have them go on to the website and find the times, the final times, and do parallel box plots. So they have the distribution of the men's, let's say, final times in the 1 mile run, and then they have the women's in the 1 mile run. Well, where that's important is you're comparing these 2 box plots parallel, side by side, one on top of the other. And typically, men are faster than women. So what's important there is they can see The shapes are pretty similar, but the men are translated over, and you can see that the speeds were much faster for men than women. And so that happens in many, many sports. So again, like Al said, that's another important attribute of the box plots, just like the gasoline problem. We're not as concerned with the shape, but what's happening there. You can see, well, the men did better because 75% of the men ran faster than women, similar to the gasoline additive problems.
And there, in this file, there's actually places where you can compare boys and girls sending text messages.
Right. That's exactly where, yep.
And have your students pay attention to where the quartiles, where the 50% of the students are above. So you want them to get familiar with interpreting the box plot, because I think it takes a lot of time and experience in different situations before kids are actually able to do that very well.
So if you ask students in that picture Gail has up there right now, who sends more text messages, well, then they can communicate, very similar to the gasoline additive problem. You know, I think girls send more messages because 75% of the girls send more than half the boys, or whatever. You know, looking at where the first quartile is for the girls is very close to where the median is for the boys.
Good. So that's box plots. Anything else we want to say about box plots, Robin?
No, I think we're good.
All right. So I just wanted to show you one other example here, because this idea of variability is really important. I'm using a file that's called mean as balance point that comes from the building concepts work. But this notion of helping kids visualize the variability is really, I think, an important thing that we need to help them understand and learn how to do. And so here's an example of where, all right, they have these different distributions, and I'm trying to figure out where the balance point is just by looking at it. And then I'm looking at, oh, the balance point's maybe here, oh, here. And where would it be here? And then thinking about an interval, the mean plus or minus the MAD. So you're looking for kind of a sense of how the spread is happening. And once you kind of make a kind of an estimate, then you can check and you can say, oh, here's the mean. Oh, that was pretty good. Yeah, I was pretty good there. And then you can actually look and see, all right, here's the mean plus or minus the MAD. So you get a sense of an interval that can define the typical. And you can actually, in this one, you can continue to generate different kinds of data and have the kids make their estimates for each new group of data sets. And then to kind of develop that skill and that understanding of what this interval that defines typical is. And then in that sense, they can begin to see, oh, now without this, I might think these guys were outliers. But now when I have this in here, I might, let's see, that's a MAD. If I get two MADs, oh yeah, I could maybe say they are outliers. So I can begin to get a better sense, just a visual sense, of when things might be outliers and when they are not. But I'm not just guessing, I'm actually using a measure of either MAD or standard deviation away from my mean in this instance. Does that make sense? And any questions, Laura or Robin, anything to add?
No, I think we're good. Again, it goes back to the visualizations there and looking at, when you see the different dot plots, about maybe how many points are beyond the two maths and what that looks like and how it might change the distribution, especially that bottom one that you were just pointing to where there's so little variability.
Right. Okay, so let me just go back to our PowerPoint here, and then we're just about ready to turn it over to Mike. The one last piece that we want to look at here is it's really important in these days and ages that kids actually experience real data. And the census at school from the American Statistical Association, which is down here, has all sorts of, actually it has hundreds and hundreds and thousands of student data with 34 variables on each. And I kind of think that this is really a good place for kids, because what we have here is real raw data. And you notice somebody didn't put anything in here. So if you're going to look and work with this data, you have to figure out, what do I do when there's no data value in? Something is missing here. If you look really carefully, you're going to see, uh-oh, what's going on here? How did this foot length get to be 67 when all the other ones were in the 20s? Uh-oh, and this arm span is 128. What do I do with that? If I were to make plots, I'm pretty sure this would be an outlier. So I have to make a decision about how did that get there and how do I handle that. So this is just a really nice place to actually go and get cool, good data to have your students analyze, to do sampling from and resampling. But you also have to then pay attention to the whole notion of cleaning the data and making sure that the data sets that you have are all sense-making in what you can do with them. I think we're just about at the end of what we were talking about here. So, Mike, are you there?
I am, Gail. Thanks so much.
All right. I will stop sharing, and I will give my little ball. Oops, I'm trying. All right.
Thanks so much, Gail and Robin, for sharing everything today. A couple things as we wrap things up. We're really excited about the upcoming T-Cubed International Conference. It's really a great way to spend some time to explore these files a little more than in this really quick 1-hour format. And really my favorite part is, let's say that you were in a session with Gail or Robin, and all of a sudden the session ends and you still have questions. Well, they're right there, and you can actually talk to them and interact with them and ask them questions and really pick their brains. So part of my favorite part about the T-Cubed International Conference is just making connections with other really great educators. So we hope to see everyone at the T-Cubed.
Can I actually add something in?
Absolutely.
This year, we are having a whole Saturday of statistics at the T-Cubed conference. So those of you who care about stats, hope we see you there.
Thanks so much, Gail. To receive a certificate of attendance, go ahead and copy that link that's on that slide into any browser to receive your certificate. Thanks so much, Gail and Robin, for everything you shared today. We really appreciate it.
Thank you.
Thank you.